Today we are performing experiment for calorimetry, and we are using calorimetry to determine a specific heat of a metal and also to determine the heat involved or calculate the heat involved in a reaction. If a reaction releases heat, that reaction is called exothermic reaction. If a reaction absorbs heat, the reaction is called endothermic reaction. If the reaction releases heat, we don't have to see the heat, but we can measure the change in temperature of the solution or the environment. And if the temperature increases, that indicates the reaction was an exothermic reaction. For endothermic reaction, the reaction environment gets cold, so the temperature drops. So we know the reaction is endothermic reaction. So we can calculate the heat based on change in temperature, because if the heat is released, the temperature of the liquid, especially the temperature of the, if it's aqueous solution, it would be temperature of the water, is going to increase. And we can calculate based on how many degrees the temperature has increased or has decreased, how much heat was involved for the gram of the substance that we have used or the quantity of the substance that we have used. And as a result, we can also calculate that amount of the heat per mole of that substance. So if we have the heat released or heat absorbed, we have the number of moles, we can divide the heat by the number of moles to find the heat released based on the number of moles or per mole of that substance, and that is known as enthalpy of the reaction or delta H of the reaction. Delta H of reaction is how much heat is being released or how much heat has been absorbed. If the heat is released, the sign for delta H would be negative. If it's absorbed, it would be positive. That is going to be part B of the experiment, please. We look at the, yes, that's basically part B of the experiment, when we are going to measure the mass of the salt, and then we find the initial temperature of the water and final temperature of the water, and based on the amount of the heat being released, we can calculate the delta H for the reaction. So heat in general, the amount of the heat released or absorbed in a chemical reaction equals heat equals mass times a specific heat times change in temperature. What is change in temperature? Change in temperature is the final temperature minus the initial temperature. Initial temperature. And since the reaction is taking place in aqueous solution, we are going to measure the initial temperature of the water and final temperature of the water that is being warmed up or cooled down as a result of a chemical reaction in that aqueous solution or in that container, or the simple calorimeter that we are going to set up today. So this is the final temperature of the solution or the mixture, and we are going to assume so that's how we find the delta T. The specific heat, we are going to assume that to be just like a specific heat of water, because the solution is an aqueous solution. So for water is going to be 1 calorie per gram per degree Celsius. What is a specific heat? A specific heat is the amount of the heat needed to increase the temperature of 1 gram of substance by 1 degree Celsius. So if we have 1 gram of water at 10 degrees Celsius and we want to increase the temperature to 11 degrees Celsius, for every gram of the water, we need 1 calorie of heat. Now, with 1 calorie of the heat, we can increase the temperature of 1 gram of water by 1 degree Celsius. This number is not the same for every compound. It's a compound specific. For example, for water is one number, which is given. For aluminum is a different number. For copper is a different number. And we can actually calculate that. We can actually find out based on today's part A of today's experiment, which I'm going to explain how you would do the calculation also. So if this number is only for 1 gram and is only for 1 degree Celsius, the more mass you have, so if it's for 10 grams, you would need 10 times as much heat. If you have 100 grams, you would need 100 times as much heat. And it also depends on delta T value, and what the delta T value is, again, change in temperature. So if you want to change it by 1 degree Celsius, the amount of the heat is required is going to be less than if you were going to change the temperature by 5 degree, by 10 degree, by 20 degree or more degrees Celsius. The more, the greater the change in temperature, more heat is needed. So we can do 2 things. We can say, okay, we have a gallon of water. We find the mass of the water and say, how much heat do we need to increase the temperature by 10 degrees Celsius? If we have a huge tank of water, how much heat do we need to increase the temperature by like 5 degrees Celsius or by 20 degrees Celsius? Or that's like more of a chemical engineer's job. Let's say you have a pool and then the equipment that you are buying to increase the temperature, what should be the capacity or what should be the size of that transformer, or how much is going to be, how much electricity is needed. So they buy like bigger unit or smaller unit as a heater or as the cooler. That's not what we are going to deal with. We are dealing about some of the reactions that by nature they are exothermic. You have 2 test tubes, let's say 2 test tubes with the chemical A and chemical B. You mix it together. Both of them are at room temperature at 25 degrees Celsius. You mix it together, and then after the chemical reaction is taking place, you measure the temperature here. It goes up from 25 to 40 degrees. Or 38 degree. So if the temperature increases, we define that reaction as exothermic reaction. And we can calculate how much the temperature has increased. We can calculate or measure the mass of the 2 liquids, how much it was. And then if we have the specific heat, we can find the value for heat needed, or heat being released, or heat being absorbed. Heat is absorbed, again, I'm just repeating myself, heat is absorbed for endothermic reaction. The temperature is going to drop, but heat is released for, did I say it opposite? Heat is released for exothermic reaction. The temperature goes up. Heat is being absorbed for endothermic reaction, and the temperature is going to drop. So there are some definitions that you are going to learn by performing this experiment. So for part B of the experiment, that's the formula you're using. And for part A of this experiment, you're actually using the application of this definition. What happens in part A of the experiment? For part A of the experiment, you are going to determine a specific heat for piece of metal, or a specific heat for metal. So what you are going to do, the general procedure is this way. You are going to heat up the metal to high temperature, and you drop that, or you pour into a cold water in the calorimeter. And why we have to use calorimeter, I will explain that. I'm just going to go over the theory first. So after you transfer hot metal into cold water, the heat is going to be transferred always from hot to cold. So metal is going to lose heat, water is going to gain heat. Now, based on the theory, the amount of the heat that is released by hot metal is going to be equal to amount of the heat that cold water is gaining. So heat lost by metal is going to be equal to heat gained by water. The amount of the heat being released or the amount of the heat that an object can hold, it depends on heat capacity also. So if heat capacity of water is 1 calorie per gram per degree Celsius, water has very high heat capacity. So you know, water, it takes time for water to get warm. Like if you have like 5 days in a row cold weather, and then one day is really hot, by end of the day the pool may not be hot enough, because that one day warming up, it wasn't enough to warm up the water, because water has high specific heat. And what does it mean? If something has high specific heat, that means it takes more heat to warm up, to increase the temperature. So if it has high specific heat, water has high specific heat, that's a good example for it. It is going to take longer to heat up, or it requires more heat to increase the temperature. At the same time, when it's losing heat, it's going to lose more heat. If the temperature is going to drop, it's going to lose more heat. So if the water of the pool it's warm, and you get only one cold afternoon, that water is not going to cool off, because it takes much longer for the heat to be released. So that's where when you are closer to to ocean, also it kind of affects the change in temperature is not like very significant. And the temperature of the water is change in temperature of the water is not as significant as the change in temperature of the air. So the air can get hot and cold like suddenly and quickly, but it takes longer time for water to lose heat or to gain heat. So change in temperature in water is less significant because it has higher heat capacity. So let me read your questions. Everything changes once the water has other properties, for example, salt, like the ocean. Exactly, yes. The specific heat for pure substance is a fixed number, but if you have high concentration of other components in the water, that is going to be different number. Exactly, yes. It's not going to be the same. The more concentrated it is, it takes more heat to change the temperature also. So yes, you're right, it's going to be different. So heat lost by metal is going to be equal to heat gained by water. Okay, I hope you can see the board. Ready? So heat lost by metal is going to be equal to heat gained by water. So heat lost by metal, the heat always is mass times specific heat times change in temperature. So heat lost by metal is going to be mass of the metal times a specific heat for metal times change in temperature for metal. That equals heat gained by water. We also have the same formula. We are using the same formula for water. So it's going to be mass of water times a specific heat for water, or C value, whatever the procedure gives you, a specific heat for water times change in temperature for water. So this is now an equation. It's an equation, and when we perform the experiment, this value is going to be measured, right? How do we measure that? Is the mass of the test tube. First, you measure the mass of test tube. You add the metal to the test tube. You measure again. Then by subtraction, you get the mass of the metal. So we find this by experiment. By experiment, you are going to find this mass. When we follow the procedure, we are going to find this value. A specific heat for metal is unknown for this experiment. For part A of the experiment, the specific heat of the metal is unknown. Change in temperature of the metal is going to be final temperature for metal minus initial temperature for metal. So the hot temperature or hot water or the hot metal before mixing has initial temperature, and then after it cools down, when you leave it in the water, it's going to reach the same temperature. When it reaches the same temperature, basically the final temperature for water and metal is going to be the same, because when you mix a cup of hot water with a cup of cold water, the heat is going to be balanced out. The hot water is going to cool down, the cold water is going to warm up. Same thing here. When hot metal mixed with the cold water, the heat is going to go from metal to water. So metal is cooling off and the water is warming up. So we find this for the metal. Mass for water, if we get, since we know the density and we did use the density last class, if we use 100 milliliters of water, that is going to be 100 grams of water, right? For water. Why 100 milliliters equals 100 grams? Because density for water is 1, density for H2O is 1 gram per milliliter. So every gram is 1 milliliter, or every milliliter is 1 gram. So using 100 milliliter, that would be 100 grams of water. Or you can measure the mass. You can use the density, or you can pour the water and measure the mass. So we get this from by experiment also. This number is a given number, 1 calorie per gram per degree Celsius. So a specific heat for water is a given number that is not unknown. And the change in temperature is going to be determined by experiment again, and that is the final temperature for water minus initial temperature for water. So you have one equation, 6 variables. You can either determine some of them by experiment, or this case, a specific heat for water is a given number. You have 5 of them. You can find the specific heat. So basically, you divide both sides of the equation by, mass of the metal times change in temperature for metal. So you divide both sides by that, change in temperature for metal and mass of the metal. If you divide both sides, then you end up with the value for a specific heat for metal. It's going to be mass of water times a specific heat for water times change in temperature for water divided by mass of the metal times change in temperature for metal. Okay. Do you have any questions about the calculation? How we are going to perform the calculation? Are we fine with the performing calculation? So you are using the concept of the heat lost by the metal equals heat gained by water. You have the formula for heat that is lost by metal, because the amount of the heat being transferred, it depends on the mass, depends on a specific heat, depends on change in temperature for metal, and the same thing for water. So if you have one equation, one unknown, and you can solve that equation in order to get the specific heat for metal by calculation. At the end, the change in temperature determines whether or not, yes, yes. Okay, and also we are going to really look for the value for a specific heat in this case. For part B, if the temperature goes up, we know that the value for delta H is negative, because by convention they get they assign sign for delta H for exothermic reaction to be negative, for endothermic to be positive. Or whenever heat is released, delta H is negative. When it's heat absorbed, delta H would be positive. Okay. If everything on the board is in this, your screen, if you can see it, you can take a screenshot of it. So just the experiment actually explained this, but I put it in different order. I think, to me, if you already had like just simple math, is going to be easier. Yes. Okay. Now, experimentally, how we are going to perform this experiment, we are going to, and what we are going to use, we are going to use a calorimeter today. The calorimeter that we are using is not a perfect and fancy calorimeter. We are going to build our own calorimeter here. We are going to use a coffee cup. And why coffee cup? Because coffee cup is a good insulator of the heat. That's why you drink your hot beverages in a coffee or styrofoam cup, because it doesn't transfer the heat easily. And we place that because it's light weighted. If I leave it on the bench top and I place the thermometer in, the thermometer could be heavy for that, and it can drop and spill the chemicals. So in order to prevent that, I'm going to place that in a beaker to make sure that it is secure in a beaker. We are using a digital thermometer. We are using digital thermometer. I want to test the thermometer first to make sure when I'm touching, the temperature is going up. Sometimes this is like, if it's reversed, we have to fix it, we have to adjust it. I just want to make sure my digital thermometer is working. So styrofoam cup with this thermometer is going to act as a calorimeter. And what we are using calorimeter for, we want to see how much heat is being released. And since that heat is going to increase the temperature of the water that is in this cup, the styrofoam cup, we don't want it to be released out. So that's why we cannot use a glass container, because glass is not a good insulator. The heat can be released to environment quickly, just like a glass cup. It gets very hot or burns your hand if you put like hot coffee in glass cup. So we keep that in a calorimeter. Now I need your help with the procedure. So tell me what to do first. We are performing experiment 1 first. To perform experiment 1 first, we need to get the mass of the empty test tube. To get the mass of empty test tube, I'm going to use a beaker to place it on the balance is a good practice, because later on, if I cannot hold on to the test tube, I have to leave it flat, and if I leave it flat, it can roll out of the scale, or some of the metals that I have in there, it can spill out, and then by collecting, I may not get everything in. So I use a beaker, and I press the tare button, just like how we measured the mass before. Press the tare, I get it 0. Now I'm going to place the test tube inside. I want you to take a screenshot of what you see on the scale. Let me know if you could see the number. Take a screenshot. You got it? Okay, everybody needs to take a screenshot of this number now. Okay, that gives you the mass of the empty test tube. And why I want to take a screenshot? Because I want you to include that into your lab later on, because for online class, I know everybody attends the online class, everybody pays attention while we are doing the experiment here, but I want to make sure that, you know, we have proof for people who are not in class, we have proof for people who are in the department. I want to make sure that they know my students are paying attention while they are watching the experiment, and they actually record the data themselves. So it's good practice for all online classes to have a checkpoint. If we have a student who is logged in, joined the meeting now, and did not get the screenshot, we're going to have like 4 of these screenshots, and then screenshots. So you have at least like 2 or 3 of them. You cannot say for the first screenshot I was using the bathroom, and the second one I was trying to get a cup of water. So you should have at least like 2 of them for you. So you would upload later on. I'm going to have like assignment folder for picture files or screenshots of the experiment. These screenshots, please do not share with everybody in class or other people in class. Everyone should get their own screenshot. It's an image. And since it's an image, when we do analysis, we are going to find the time that this actually picture was taken. We can prove that. And then it has to be class time, because if you watch the video later, you could also do a screenshot. That's not valid. So a screenshot needs to be taken during the time. I should have explained that before, you know, we actually use it, but it's okay. We are going to practice that off and on in the lab, and at least every lab I'm going to have like 2 screenshots to make sure students get at least something.
But Professor, if we have the data sheet, I prefer to write it down than take a screenshot and then not understand what it says.
Okay, data sheet is for your grade. A screenshot is a proof for your presence, that you actually physically sit down by the computer when you are doing the experiment.
Are my messages to you not enough during the class?
Yes, if you're talking, you're responding is enough, but how many responses do I get when I'm asking questions?
Okay.
Is that does it make sense? This yes. Yeah. Because I don't get response of 18 or 19 students, everybody's response, and we want to make sure that everybody attends the class and actually don't, you know, it could be, it doesn't happen to my classes because my students, they actually like to attend the class. They ask questions during the class, and we all enjoy that each other's interaction with each other. But there could be like online class, logs in, joins, and then leaves and comes back later, leave the session, and then watch the recording later or just get the data. So we want to make sure that this is actually live. So we take screenshots not too often. And the picture doesn't have to be perfect, okay? We got to keep it very simple, and it's not going to be, So,
okay, Professor, do you want us to turn in the screenshot when we turn in our assignment?
Exactly, yes.
Okay, alrighty, thank you.
You're welcome, you're welcome. If that was the question, I'm sorry I didn't get it the first time. But at least, you know, I just wanted to also make the point that why we are doing this, and it's not, you know, it's not saying that people are not, but it's just to prove that everyone is actually attending and paying attention to this. Okay, what's the next item in the procedure? You want to fill the test tube and measure the mass again, right? We want to fill it up to like a half. I don't want to make it 2/3 because it's going to be heavy. The metal that I use is the copper, and I put some metal into the test tube, and I'm going to weigh it again. When I weigh it again, I want you to record that number. Is 57.45. Do you want to take a screenshot? So in case you missed the last one, you have one, this one. Okay. Take a screenshot of the scale, please. And the number shown there is 57.450. Did you get it? Yes? Perfect. Perfect. The metal is copper, yes. We had choice of two. It was either the zinc or copper. I used the copper for today's experiment. Then we are going to place this test tube inside the hot water for 5 minutes. Gonna time that, leave it there for 5 minutes. And 5 minutes should be enough time for the heat to be transferred to the metal and the metal to get hot. Actually, it reaches to high temperature. So we're going to time for 5 minutes. Do you have any questions while we are waiting for 5 minutes, or should I get ready for the next chemicals for the next steps?
Professor, a question. For
Sure.
the time that you want to do the water, is that E?
Is the time or the temperature? The time is not recorded there. That time is based on the procedure. But let me go to the data sheet. So we have the massive empty test tube. That's B. Metal uses copper. Massive empty test tube. You had the first screenshot. I don't have that number, so we get it. If you missed it, we get from someone now. Make sure you have it. Mass of the test tube and the metal, that was the 57.45. And then E, initial temperature for water. Initial temperature for water is going to be, first, based on the procedure, we are going to take 100 milliliters of water, 100 milliliters of water.
Amaya, turn off your mic. It's switching.
Thank you. We take 100 milliliters of water. We place into in the styrofoam cup. Was that 100 or it was less or more? Do you know if it's 100? 100 milliliter, okay. Of deionized water, and when we record the temperature for this water, that's the initial temperature for water. And that is, let me use the decimal so I can get the, it's 25.5 degrees Celsius. This is the initial temperature for water. 25.5. You got it? 25.5 was fluctuating between 5 and 6, but we can use that. 25.5. Let's see if this one works. Okay. What else do we need there? Then you need the maximum temperature after mixing. We haven't mixed it yet. The rest for the data sheet part A is just the calculation. So it's calculating the change in temperature for water. That would be initial temperature subtracted from the final temperature for water. And then do you know what is that 100 minus F by any chance? Why is it 100 minus F? F value is the final temperature of the mixture for water and for the maximum temperature. Yes, very good. So it's the 100 minus the value for F, or the maximum temperature, is assumed that the temperature of the metal, it would reach 100 because it's in the boiling, is inside the boiling water for 5 minutes. But to make sure, we can always measure that number. And we can, if it's not 100, we can change that number. But I don't want to confuse you guys. Oh, even though it is like, no, it's good. It's good. It is 100. So that 100 is basically initial temperature for metal. And then the maximum temperature when you mix it is going to be the final temperature for both metal and the water. Okay, do you have any concerns, any questions at this point? Has it been 5 minutes? Not yet? Okay, thank you for keeping track. It's been 5 minutes? Okay, if it's 6:12, then okay, don't worry about that timing. Don't worry about it because since you have a 6:09 and 6:12, I'm just going to wait extra minutes so we can we make sure that it's going to be hot. It's not going to, the temperature inside the test tube is not going to be higher than the temperature of the water. But if we take out early, that temperature could be less than temperature of the hot water. So it's better to be safe, so we can keep it for longer. Okay, so we can keep it for longer. So just in 30 seconds, we make sure that we have more than 5 minutes. So this is like at least 5 minutes. So in 30 seconds, we would have more than 5 minutes of the time. Because the test tube is hot, I'm going to use a test tube holder to take the to hold the test tube to transfer. And because this test tube is heavy, sometimes if I lift it up and transfer to the calorimeter, it might slide because it's heavy. So I'm just going to bring the calorimeter closer and add the metal. So for initial temperature, you have 25.5, right? The temperature now is increasing. The temperature now is increasing, and I will let you know what is the highest temperature that can reach, and we record that temperature. Okay, the highest temperature is 28.0. So the final temperature is 28.0. That was the maximum temperature that reached. If I wait longer, of course, because it's open, the temperature is going to go down. So there's really no need. When I see that highest number, it was the 28.0, I can record that number. And is that for F? Yes. Yes. Okay. That's for part A of the experiment. Part B of the experiment, going to move the hot plate somewhere. For part B of the experiment, what is that we need to do? You want to help me with part B? For the procedure, ten milliliters of DI water in a styrofoam cup. So we get 100 ml of water, styrofoam cup, and we place the styrofoam cup in beaker again. We do need to measure the temperature for that. Yes, negative 2.5. Take the aluminum dish and measure 12 grams of calcium chloride, 8 grams of ammonium nitrate. Nitrate. 8 grams. So we need to measure 8 grams of the ammonium nitrate. So I'm going to place the aluminum pan first. Here, add enough to make it 8 grams. Okay. So I have 8 grams of aluminum nitrate.
Professor, I have a question about the previous. Why is the temperature negative? Because the initial temperature of the water was 5.5 and the final was 28. Why is it negative? Is it not final minus initial?
Final minus initial for water is going to be positive.
Correct.
For metal is going to be negative.
Oh, okay,
right?
yeah. For water is positive.
Yes, for water is positive.
All right.
So for metal it's going to be, and then if you define, if you put that in a definition that heat is being lost, so it's just a change in temperature. So you could actually use the absolute value, but based on definition, when the heat is lost, they give like a negative sign to it. That means the temperature has been dropped. So don't worry about the positive or negative sign. You could use the absolute value for your calculation. Okay, we have the temperature of the water showing in here. Should you take a screenshot or take a screenshot in case if you missed the last two? Now you have these numbers. That's the value for initial temperature of the water before adding ammonium nitrate. The mass for ammonium nitrate is 8 grams. Now, I'm going to add the 8 grams of ammonium nitrate, and I want you to monitor that temperature. What is happening here? Temperature increasing or decreasing? Can you see? The temperature is decreasing. And we are going to wait until it shows like stable temperature. Basically, we want to record the lowest temperature that was produced after being stable. Okay. At this point, whatever temperature that is stable, we can record it. $18.9. You can take a screenshot or you can record. If you already have a couple of screenshots, you can record this. 18.9. So we start with 24.5 and we went down to 18.9. So reaction or the solubility or dissolving of ammonium nitrate in water, is that exothermic or endothermic? The temperature dropped. So the temperature of the water at the beginning, the temperature of the water was 24.5. When we added the ammonium nitrate, the dissolving of ammonium nitrate, it took heat from the water, so the temperature of the water dropped. So this process is called the endothermic process or endothermic reaction, where the temperature drops as a result of a chemical reaction. Did you record the number? Because I didn't, and now it's warming up. So it was 18.9. Thank you. Thank you. Okay. So initial temperature was 24.5 and the final was 24. No. This was, everything was just for just the first column or the second column. If you look at the data sheet, what you have here. For part B, check the data sheet, please. That's the last page. Check the data sheet. So the first column is calcium chloride. We haven't done anything with calcium chloride yet. The second column is the ammonium nitrate. That's the second column. It's best if you have the procedure and that or data sheet at least printed for you, so you can see and match the data with where it goes. So you have the mass of the salt, which was 8 gram for ammonium nitrate, or did I make a mistake? I think I followed the procedure exactly the way it was, and it's asking for 8 grams of ammonium nitrate. So I had the 8 gram for ammonium nitrate. That goes to the second column. Then you go to D. So you fill A with mass of the ammonium nitrate. That was 8 grams. Then you go to D. That is 24.5. So that is the letter D. The final temperature for F, for the second column, is 18.9. 18.9. So let's just collect the data value. Then I helped you with the calculation, like how do you find the formula weight of the salt, because it may not have, you have not probably not covered in lecture yet. So we're gonna pull periodic table, and I show you how to do the calculation. But let's finish the experiment first. The second part of the experiment, which is the first column on the data sheet, last page of the data sheet. This is for calcium chloride. What we need to do first for calcium chloride, we need to measure 12 grams of calcium chloride first. $12 grams of calcium chloride. So I'm going to add enough to make it 12 grams here. Since this is given by the procedure and it must be 12 grams, you could just trust me, I'm actually measuring 12 grams here. Okay, so this number now is 12.005, and the last digit being like uncertain digit. So you have 12 grams of calcium chloride. So you must have at least 2 screenshots. If you didn't have a screenshot, you don't have to. Please take a screenshot of this so you can use that. And we are going to get 100 milliliters of water. Use the beaker again. Transfer 100 milliliters of the water into a styrofoam cup and place the thermometer into the water. Trying to measure the temperature before mixing, and this temperature is again 24.5. It's kind of moving. 24.5. 24.5. You could record for it. This is the initial temperature for calcium chloride. Then you have 12 grams of calcium chloride. This is the mass for calcium chloride. In case if you didn't record it, make sure to record it. Now I'm going to add the calcium chloride into water, and you can see the change in temperature. See, I don't have any hot plates or Bunsen burner here to heat up this reaction, but the temperature of the water is going up. The temperature of the water that is going up is coming from this reaction. What type of reaction is this, exo or endo? This is the exothermic reaction because the temperature went up. And the final temperature that is stable at this point is a 39.4. 39.4 is the final temperature. That was the highest temperature, and you record that as 39.4. This is just for the calcium chloride. Okay. Now, for your data sheet, for part B of the data sheet, is asking for formula weight of the salt. How do you find the formula weight for calcium chloride? Was it 0.4? Okay. Now, the formula weight for calcium chloride. You have the formula, molecular formula for calcium chloride. You look in periodic table, and in periodic table, the mass for calcium, the atomic mass for calcium is 40. That comes from the periodic table. It has some decimals, but we just rounded up to 40. And then for chlorine is 35.5. But since we have 2 chlorines, we are going to multiply by 2. So it's going to be 40 plus 35.5 times 2. So it's going to be 71 plus 40, 111 grams per mole. That would be the formula weight for calcium chloride. So in order to get the formula weight for a compound, you take each element, you get the atomic mass for each element, and you multiply by how many of that element you have. So for calcium, since you have only 1 calcium, this would be 40 times 1. For chlorine, because you have 2 chlorine, would be 35.5 times 2. And then you add them all up, and that would be the formula weight for calcium chloride. What does it mean? It means if you have 1 mole of that calcium chloride, it would weigh 111. Yes, I did round it up to 40 for calcium. If you don't want to round up, I don't have the exact number. So you can use the exact number if you want it. But it's okay to round it up. Now, the other one, you have ammonium. The other compound, you have ammonium nitrate. Same way, we're going to follow this. Nitrogen is 14. Hydrogen is 1. This nitrogen is 14 and oxygen is 16. These numbers are rounded up number from periodic table. That is the atomic mass for each of these elements in the periodic table. But when we are trying to find the formula weight for this compound, we have to multiply this number by the subscript that it shows how many of the hydrogens or how many oxygens you have. So 14, I can say 14 times 1 or just 14 plus here we have 1 times 4 because we have 4 hydrogens plus we have 14 times 1 for 1 nitrogen that we have. So this is coming for hydrogen, that's your nitrogen, plus 16 times 3, that is for oxygen. Oxygen is 16 times 3, and it's going to be 32 and 48, 90 grams. Yes? Okay. Was it 90?
Yeah, it's 90.
Thank you. 90 gram per mole. Perfect. So we have the formula weight for ammonium nitrate. We have the formula weight for calcium chloride. And then you want to find the moles of calcium chloride and moles of ammonium nitrate. How do you find number of moles? Number of moles for calcium chloride equals mass divided by the formula weight or the molar mass. It's the same thing, molar mass. So what is the mass of calcium chloride? Mass of calcium chloride, we measured 12 grams. You divide that by the molar mass for calcium chloride was 111 grams, and you find the number of moles.
Professor, I was wrong. It's 14 times 2 plus 4 plus 16 times 3. It's 80.
80? Okay, thank you.
Yeah, I think both calculated 14.
Yeah, 32 plus 48. Okay.
Yes.
80. Perfect. That's good. So it's 80. Now, number of moles. To calculate number of moles, you divide the mass by molar mass. Where do you get the mass from? The scale or the procedure? It tells you to measure 8 grams, 10 grams, 12 grams. Molar mass, it comes from periodic tables, which is the numbers that we did the calculation for. So number of moles for the other one, for ammonium nitrate, is going to be 8 grams. We measured 8 grams. 8.00 grams divided by 80 gram per mole. Gram per mole. So whatever number you have here, so this is going to be 0.1, right? It would be 0.1 moles of ammonium nitrate. So it's going to be 0.1 for this one, and for the top one, just use your calculator. Is it 0.108? 108. So because I'm not sure if the lecture already covers how to calculate moles and how to calculate molar mass, I want to make sure you know how to do the calculation for your data sheet so you don't struggle later on. Any other questions from the data sheet? Units for, yes. Yes. You got it. What is B? I don't know which B. Are you talking about the part B of the experiment, heat of solution, or you're talking about B as a formula weight of the salt? Oh, formula weight of the salt. This is B. That's for the calcium chloride. Yes, we did do the calculation. This is the B and this is B. So each one goes to one column. This is for formula weight for calcium chloride. This is the formula weight for ammonium nitrate. So we have all the numbers. When you are labeling A and B, just make sure that you have is basically not A and a B, is the B for calcium chloride and is B for ammonium nitrate. Yes. Okay. Any questions? I'm going to stop recording, and I'm still answering your questions. We still have time at the lab. So I just, because we are done with the experiment and data collection, I'm going to stop the recording. And this way I can call for attendance.